So hopefully you all know that my name is Alyssa Allen. And my presentation this morning is on the utilization of receiver operating curves, known as ROC curves, for the evaluation of fire debris, and more specifically, how population distributions can affect classifier performance. First and foremost, I'd like to acknowledge and thank the National Institute of Justice for the support in funding this project. So one of the major challenges in fire debris analysis, as you are all aware, is determining whether a sample contains ignitable liquid residue, especially when a substrate matrix is present. Casework samples are analyzed using the ASTM E1618 protocol, as you all are aware, through known comparisons of ignitable liquid subclasses or categories. This allows for the fire debris analysts, all of y'all, to report on whether a sample contains ignitable liquid, denoted as IL, or is absent of ignitable liquid, which can also be characterized as a substrate or sub. Now, one way in order to strengthen the reportings of these categorical statements is to calculate likelihood ratios. Now, previous research that utilized these likelihood ratio calculations for this classification problem used chemometric models such as support vector machines, quadratic discriminant analysis, k-nearest neighbors, and linear discriminant analysis. These chemometric models were based on computationally balanced data sets in order to evaluate the method performance of real fire debris. By using chemometric models, we're able to generate receiver operating curves, or ROC curves, which are characterized by their true positive rate as a function of their false positive rate. By generating these ROC curves, you're able to calculate an area under the curve, which is the probability that a randomly chosen positive sample, in this case ignitable liquid, would have a higher score than a randomly chosen negative sample, in this case substrate. So basically, area under the curves closest to 1 correlate to the better discrimination of that model. Now, when these chemometric models were evaluated using cross-validation, they calculated relatively high area under the curves. However, when these same chemometric models were utilized to evaluate real fire debris, overall, their area under the curves significantly decreased. Now, there are possibly two main reasons for the decrease in classifier performance when evaluating the real fire debris. The first is that the trained data might not have been representative of the real fire debris. With that being said, either there was not enough substrate data in those computational models, or there was not enough exploration in the differing of those ASTM ignitable liquid classifications. The second is that there was a different ground truth assignment between the computational data sets and the real fire debris data sets. Computational data sets were assigned ignitable liquid if they contained 1 to 100% of ignitable liquid, whereas the real fire debris data sets were assigned ignitable liquid by an informed analyst who had prior knowledge of the ignitable liquid used, as well as the for-trail location. Therefore, these new models, to strengthen them, they will include more substrate data. They will be calibrated so that their predictions will be proportional to the frequency of occurrence. When evaluating the real fire debris, there will be a relaxed ground truth assignment, so there's not actually known ground truths for either class representation, ignitable liquid or substrate. And also different population distributions will be explored. Now, the way in which these likelihood ratios were calculated is through a one-level or a single sample measurement model, in which the numerator is representative of ignitable liquid, in which C1 and X bar 1 are the covariance matrix and the means for the ignitable liquid class, respectively, and the denominator is representative of substrates, in which C2 and X bar 2 are the covariance matrix and the mean for the substrate class, respectively. Now, there are two approaches when taken for this research when calculating the likelihood ratios. The first approach is to assume that the covariance matrices for ignitable liquids and substrate class are the same, in which the shapes of ignitable liquids and the shapes of substrates are the same, and they can be separated or discriminated by a line or a linear discriminant analysis. The second approach is to assume that those covariance matrices are different, in which the shapes for ignitable liquids and the shapes for substrates are also different, and they can be discriminated or separated by a quadratic equation or quadratic discriminant analysis. Now, these data sets were computationally simulated by in silico total ion spectrum mixing in which one ignitable liquid was mixed up to 5 substrates consisting of 0 to 99%. All total ion spectra was base piece normalized and also contained an additional 10% randomly distributed noise. Now, these data sets were comprised of 10,000 total ion spectra, or 10,000 samples, and that was derived from 445 unweathered and 244 weathered ignitable liquids found in the ignitable liquid reference collection, and an additional 111 substrates to the already 122 substrates found in the substrate database. So, out of these 10,000 samples that comprise these data sets, 90% of that will be kept to train the model for each population distribution, and 10% will be kept for testing or cross-validation. So a 10-fold stratified cross-validation method was used in order to evaluate 6 different population distributions. These population distributions differ between being balanced and unbalanced, as well as differing within those ASTM ignitable liquid classes or categories. For example, distribution A is a balanced data set consisting of 50% ignitable liquid and 50% substrate. And their ignitable liquid classes are equally distributed. Each class consisted of 6.3%. Whereas distribution F is also a balanced data set. However, it only contains 50% gas and no other ignitable liquid subclasses. Now, once again, that 90% that was kept to train the model then underwent principal component analysis, and 90% of that variance was kept. Then likelihood ratios were calculated using that single sample and measurement model, and with both approaches, QDA and LDA, those likelihood ratios were then converted to log likelihood ratios, and they were calibrated using pooled adjacent violators. Then that 10% that was used for testing was tested to generate receiver operating curves, and that was repeated 10 times. So basically, for each population distribution as the model, it generated 10 ROC plots, and each ROC plot consisted of 6 curves for each testing data set that was for those population distributions. Now, once an optimal population distribution was determined, that was used to evaluate the real factor rate. So here's an example of one of the ROC plots using the QDA approach with population distribution A for the model. As you can see here, that there's small variance between each population distribution as the data set. Looking at an overall picture with these box plots, you get a small range of an area under the curve from 0.965 to 0.985. So you get an overall average of 0.975 plus or minus 0.004. When looking at a summary of all the QDA data, you can see here that you generally, for the QDA approach, regardless of the population distribution as the model or between those testing data sets, relatively you get a fairly high area under the curves. However, there's slight difference between which population distribution was used as the model. Once again, looking at population distribution A as the model, you see here you get small variances between each data set. However, when looking at training F, so looking at the population distribution F as the model, you can see here that there's a larger variance between each population distribution as the data set. Now, this can be attributed to the fact that population distribution F was not representative of all of the testing data sets because it only contained 50% gas and no other ignitable liquid subclasses. Now, one way in order to determine a model's discriminating power, calibration, and accuracy is to look at their detection error trade-off plots, their empirical cross-entry plots, and their tippet plots. Now, when looking at, once again, the QDA approach using model A, you can determine discriminating power by looking at their DET plots. DET plots are characterized by their false negative percentage as a function of their false positive percentage. So basically, the closest this curve is to the origin correlates to the better discrimination of that model, so the less misleading evidence. To determine the amount of misleading evidence, that is done by determining where this curve intersects this diagonal line from the origin. By looking at both the x and y axes, you can determine an equal error rate. For the model distribution A, you get about less than 10% of misleading evidence, which is fairly good for a model. You can also determine discriminating power by looking at tippet plots, in which you can determine that by where these two curves cross this vertical dashed line, which correlates to a log likelihood ratio of 0, which is in mutual agreement for either class. The right curve is representative of the liquid class, and the left curve is representative of the substrate class. You can determine misleading evidence for each class by where those two curves cross that vertical dashed line. When looking at the liquid class, you can determine the amount of misleading evidence by looking at the y-axis, and you can determine that once again it shows less than 10% misleading evidence. You can also determine calibration and accuracy by looking at BCE plots. You can determine calibration by the distance between these two curves. The red curve correlates to the calculated likelihood ratios for the model, and the blue curve correlates to the optimal calibrated likelihood ratios using pool-reduced and violators. The closer these two curves are, so the smaller the distance, the better calibrated your model is. As you can see here, these two curves have a small distance, so the model is fairly calibrated. You can also determine accuracy by the distance these two curves are to the x-axis. The closer they are to the x-axis, the more accurate your model is. So when looking at QDA with the training model A, you can see here that not only is it fairly calibrated, it's fairly accurate. Now here's an example of one of the ROC plots using the LDA approach with model distribution A as the model. Now there are two things that you can notice. One, once again, there is small variance between each testing data set, but also because these curves are further away from the upper left quadrant, you get a decrease in the calculated likelihood, decrease in the calculated area under the curves. When looking at the overall variance, the range between each testing data set, you get a range of about 0.86 to about 0.90. You get an overall average of 0.879 plus or minus 0.10. Now here is a summary of all of the LDA data. Now you can see here that there's vast differences between which population distribution you use as the model. For example, once again looking at population distribution A as the model, you get pretty small variance between your testing data set and generally relatively high area of curves. However, when you use training F as the model, not only do you get a large variance between each testing data set, but you even get really low area of curves, as low as 0.664. Once again, that could be attributed to the fact that population distribution F only contained 50% gas in its model, and so it might not be representative of the other testing data sets. Once again, looking at their DET plots to determine discriminating power, this curve is further away from the origin, so we'll suspect that it will have more misleading evidence. Once again, determining where this curve intersects this diagonal line, looking at the x and y axes, you can determine that you get about a little bit over 20% misleading evidence, which is relatively higher than the QDA approach. Once again, looking at the Tibbet plots to determine about the same thing for the class representation of ignitable liquids, you can determine that you also get a higher misleading evidence, over 20% for the ignitable liquid class, using the LDA approach. Now, when looking at ECE plots, you can see here that there's a small variance still between the two curves. However, these two curves are further away from the x-axis. So in comparison to QDA, it's about the same calibration, but it's less accurate. Now, it was determined that population distribution A was the most optimal, and that was because it generated or calculated relatively high area on the curves with small variances between each testing data set. So that was used in order to evaluate row fire debris. So with this class representation, if you're able to calculate likelihood ratios for your own fire debris, you can generate and project that onto your ROC plots, and a fire debris analyst would then be able to determine that if, depending on whichever approach, that if your log likelihood ratio was less than 0, you would then assign that to be a substrate, and if it was greater than 0, you would assign that to be ignitable liquid. Same thing for the LDA approach. Now, we used a very limited validation study with known ground truth samples, 16 of them, 8 being ignitable liquids and 8 being known ground truth substrates. When we evaluated using, once again, population distribution A for the model and with both approaches, it was determined for QDA that we had an accuracy about 13/16, which is about 81% correct, in which 2 substrates were misclassified and 1 ignitable liquid was misclassified. When we then evaluated using the LDA approach, we had a more accurate system, 14 over 16, so about 87%, in which there was a misclassification for each class, and then liquid and substrate. So that being said, it is important to make sure that models, or when you're training, that you have a sufficient representation from each and every liquid and substrate class, which is what population distribution A demonstrated. When evaluating computational fire debris, it seemed as though the QDA was better suited for that. However, looking at that limited validation study, it seems as though LDA might be better for real-world samples. And now the future goal, or the main goal, is to validate this likelihood ratio method in order to be used to evaluate the real fire debris.